Okay, I'm going to do an answer key for quiz 8. So the first question is select the structure of benzyl methyl ether. Oh, I'll say this is for fall 2024. This is for my organic chemistry 2 final exam review. So this is my final exam review for organic chemistry 2. And I'm just doing it as sort of like a take-home quiz. But students have to fill in, you guys have to fill in all your work, show your work, and then upload the quiz. Okay, so the first question is select the structure of benzyl methyl ether. So benzyl, if you remember, is, I like to say benzyl has a bend in it. So it's a benzene ring, but with a CH2. So this whole structure is benzyl. And when you have ether, it'll say what's on one side and then the other, and then the ether is what connects them. So the oxygen is what connects them. So it's going to have an oxygen connecting them. So this whole thing is the benzyl, the benzene with a CH2, and then on the other side a methyl, 1CH3. So this is what we're looking for. So this one's not right because it's got 2 toluenes. This one right here has benzene on one side, and this is a phenyl. So this is close, but not correct. This has methyl on one side and benzyl on the other, so I think it's C, but I'm going to keep checking just in case. I don't even know what that is, 2 benzenes and 2 benzenes. So really the only 2 contenders were 2 or 3, and 3 is benzyl because it has a bend in it. So answer choice C would be my answer there. The next compound, next question is which compound would have the lowest boiling point? So when I think of boiling point, I think of molecules. If you think of 2 molecules being attracted to one another, if there's a negative side, the positive side on one, so if this is positive and this is negative, the positive side will be drawn to the negative side of the other. And so if you think of the this is a partial negative and this side's partial positive. So if you think of how they're attracted to one another when they're in the solid state, they're really close together like this. And then as they start to get energy in, they can wiggle around and move, and they can basically kind of start to spread out. And like as they get energy, they'll start to overcome the energy that's attracting them together, the electronic attractive forces. So the energy will overcome that, and they'll start to spread out. And as they spread out, then they will keep getting more and more energy. And then when they get to the gaseous state, they have to be really far apart. So basically, however strong these attractive forces between them are, however strong like these forces that attract them to one another are, the stronger those are, the more energy it takes for them to spread out. And so basically, the more energy it takes for them to boil, because this transition is boiling, where we go from close together to spread apart. So basically, these stronger intermolecular forces are higher boiling points, and lower intermolecular forces are going to give us lower boiling points. So the less intermolecular forces is going to give us the lowest boiling point, and hydrogen bonding, which is just H with oxygen, fluorine, or nitrogen, that would have the higher boiling point, and then dispersion forces would have the lowest, so that's something completely nonpolar. And then dipole-dipole, where there's a pole, but it's not as strong of an attraction, is going to be somewhere in the middle. So when I look at all these, there's definitely a polar bond here, but there's not hydrogen bonded to oxygen with fluorine, so this is dipole-dipole. This definitely has an oxygen bonded to a hydrogen, so this is H bonding. This is also H bonding because the hydrogen bonded to an oxygen. This is H bonding as well, and H bonding. So I see all these have a hydrogen bonded to an oxygen, so all of these will have relatively high boiling points, so this one has to be the lowest. So that's how I get to answer choice A. Okay, the next question, which reaction can accomplish the following in good yield? So when I look at this, when I look at questions, it's like, oh, what reagents do we need? I try to see what is changed. And so we've gotten rid of this double bond right here. That double bond has gone away. This double bond right here. and we've added a alcohol on one side, and there must be a hydrogen on the other, because to start with we only had 2 hydrogens here and 1 here. So now there's still, the original ones are still there. The only thing we've added is 1 hydrogen and 1 alcohol. So this is, we've added H on one side and OH on the other. In other words, we've added H2O. So there's 3 ways to add water across a double bond like that, where we add OH on one side, H on the other. And I did a whole video on this, so if you want more information, you can check that out. But in the meantime, I'll just say, let's see, I'll give a quick overview of the 3 ways to add water. And they're actually listed here with A, B, and C. And so question 4 was really trying to get at this. It should be A through C were used instead. So question 4 was really trying to get at this, where the first one we have, if we have this starting material and H and H plus and H2O, that's acid-catalyzed hydration. So the alkene will attack that hydrogen, and then we get a carbocation. Whenever there's a carbocation, it can always undergo rearrangement. Oops, I did not mean to do that. Where the positive charge will go right here, and then the methyl will go here. And then, so your carbon, basically this methyl moved over to give you your positive charge there to make it more stable. I have a whole video also on rearrangement, so you can just search my YouTube channel for that. And then if you attack right there with the water, you get your OH here and your methyl here. This is initially OH2 plus, but then we just go through a deprotonation step that turns that into OH. So that's the answer we would get if we did answer choice A. So this adds Markovnikov, but it also has the possibility of rearrangement because of that carbocation. Now, oxymercuration, demercuration will add Markovnikov, but with no rearrangement. And what I mean when I say rearrangement is what I mean when I say Markovnikov is that the, I'm gonna actually add a page in. If you see the more substituted side, so like if you have an alkene here, there's 1 hydrogen here, 2 hydrogens here. So the left side, this side of the alkene, is more substituted. So if your nucleophile ends up adding on that side, and your hydrogen adds on this side, which is the overall reaction of an addition bond, that is, or an addition reaction, that is Markovnikov. If it adds the other way, where you get your nucleophile on the less substituted side, so instead of OH, I'll just write nucleophile, on the less substituted side, and the hydrogen on the more substituted side, this is anti-Markovnikov. And then the one that we saw with rearrangement is initially your electrophile does add to the more, or to the less substituted side, so that's Markovnikov. But if it can undergo rearrangement, it will, and so technically it's still by Markovnikov stereochemistry, but it just goes through the carbocation here. Your nucleophile adds eventually to that position where the carbocation was, and you get something like this. So this is still, and your hydrogen bond, or your H is still there, obviously. So this is still Markovnikov, but it's Markovnikov with rearrangement. So hydroboration oxidation will add water, not hydroboration oxidation, sorry. Oxymercuration demercuration will add water across this double bond. H to the less substituted side, OH to the more substituted side with no rearrangement. Hydroboration oxidation adds H to the more substituted, so it's the opposite, OH to the less substituted. is the opposite on this one. And then for acid-catalyzed, it undergoes rearrangement, so it still adds H to the less substituted, but it adds OH to the more substituted, and you have to consider rearrangement. So if for all of these we know that the OH is the nucleophile, then we say that this would be the product if we used oxymercuration demercuration. This would be the product if we used hydroboration oxidation. So this is for answer choice B, I think. This would be for C. Let's see. Yeah, this is for answer choice C if we use hydroboration oxidation. And this, if we replace the nucleophile with water, this would be for answer choice A. And then D is just OH minus at just a text, so it doesn't really do anything because they're both nucleophiles. So if we look at the answer choice we have here, we've added this alcohol to the less substituted side. So that must mean it's Markov-Nikov without rearrangement, so that is answer choice B. So hopefully that was a helpful review. If you're still confused, I'll have a way more in-depth video about this that you can watch on my YouTube channel, and I have also like a short video on it as well. Okay, for question 3, name the alcohol that's generated. So to name the alcohol, you have to first find the parent chain. So 1, 2, 3, 4. So the parent chain is butane. It can be numbered either way. So if I start from the side, 1, 2, 3, 4. Those are my two options, either the one in black or the one in red. And actually the one in red is better because the alcohol is 2 instead of 3. And alcohol is a higher priority, so we want it to be lower. So this is butane. And then we have 2-all. And then we have 3,3-dimethyl. So if we combine the whole thing, it would be 3,3-dimethyl butan 2-all. Okay, oxymercuration demercuration can successfully be employed for making deuterated derivatives. So what deuteration is basically it's an is it isomer? Is that the word I'm thinking? Nope, isomer is the wrong one. Isotope. It's an isotope. But basically it's just heavy H. So another way I think of it is like if we were to say it's labeled, all the hydrogens in here, instead of being just regular hydrogen, they're special hydrogens. So we label them as D. It's for deuterium. If you've ever heard of heavy water, that's what they're doing there. The biggest thing that this is testing is, do you know where the H and the OH are going to add for this question? And we just went over that anti-Markovnikov, or this adds Markovnikov, so OH goes to the more substituted side, and H goes to the less substituted side. If we use oxymercuration demercuration, because it's Markovnikov. So if I see these structures right here, we know that it's going to this is oxymercuration, so mercury and oxygen, and then oxymercuration, this is the demercuration step. So we know that ultimately we're going to add our OH to the more substituted side, and our H, which this is a special H, so I'm going to put it in red, goes to the less substituted side. And we get rid of our double bond, so that's not there anymore. So our final product looks like this with a hydrogen here. So I'm going to get rid of anything that doesn't look like that. So the first one we have, we've added an OH, but we haven't added our special hydrogen here, so that doesn't count. This one we've added the OH, but we didn't add it to the more substituted side. It should be right here. This one we added an OH where the methyl is, and we added our special hydrogen. So this deuterium is the same as the hydrogen being a special label. It's just like a labeled hydrogen. This one we added our OH, but we added it to the less substituted side. And this one, same thing, we added OH, but it's not on the same one as the methyl. So our only possible answer is answer choice C. Okay. So that would be this C. Okay. The next question, what is the correct IUPAC name for the following compound? So I'm just going to number this, 1, 2, 3, 4, 5, 6, 7. So 7 is heptane. And it has, then I'm going to find my substituents, 1 alcohol, 3 fluoro, 5 methyl. So my substituents are the alcohol, the methyl, and the fluoro. And then I'm going to combine those. So the alcohol actually goes at the end. So we get heptan 1-all. And so if you could just find the heptane chain, you could immediately, this is hexane, and this is hexane. So now we're down to either D or E. So we have heptanol, and one says heptan 7-all, and one says heptan 1-all. So just from that, I can get my right answer. But I'm going to go ahead and finish it. We combine these in alphabetical order. So it's 3 fluoro, 5 methyl, heptan 1-all is what the final answer should be. And that is what answer choice E is. Okay, question 8. If trans-2-butene is treated with MCPBA, that's a peroxy acid, so you might also see it looking like this, or I might also say peroxy acid. Sometimes people say per acids. This is going to essentially get rid of the double bond, and where the double bond was, add an oxygen, and that is basically making an epoxide. But we keep our double bonds here. We keep our substituents trans, but remember, we have to show that in 3D structure, because once it goes from being sp2 to sp3, it has 3D shape. So one of these needs to be a wedge and one of these needs to be a dash. So that's what I'm looking for. So to me, that looks like answer choice B. Now, if you want to challenge yourself and kind of go one step further and make sure that you really understand the concepts, because this is similar in the concepts to your final exam, but it's not going to be like these exact questions. So it's going to be helpful for you if you can kind of take it one step further. So the next thing I would do is see if I can make the right alkenes for all the other ones. So I would be made from a cis alkene, because these wedges are the same side as each other. C, it looks like the alkene would be like this. See, because the 2 methyls are on the left side and the 2 hydrogens are on the right side. And then for D, it looks like it'd be right here, C. This says CH2 and CH3. This is CH2, CH3. Okay, so it would look like that. So that's how I can kind of confirm that answer choice 2 is correct, and also test myself on what the alkenes would have been to make the other answer choices. So that sort of takes this quiz and then takes it to the next level. Okay, the next question, and in case you're struggling with converting these to like structures, like be sure that you know that the basics of bond line formula, and if you need to, I do have a video on like the basics of bond line formula. Okay, so we have this alkene, that's the first one, and then this is a peroxy acid. It's just like MCPBA. See how there's 3 oxygens, 1, 2, 3. That is how we know it's a peroxy acid. So this is going to essentially get rid of this double bond and turn it into an epoxide. And then we have this epoxide with acid. Whenever you see HA, you can think of H plus and H2O. That's kind of what it's trying to say. So this will attack, and you will get a protonated oxygen And then we have our nucleophile is this, the methanol, and it's going to be attracted to, as this is protonated, it's sort of pulling electron density toward it really strongly and leaving a strong partial positive behind it. So this is going to attack, and that bond is going to break, and you'll end up with something like this. So we've added our nucleophile on one side, and the other side broke open to add an alcohol. So now we just have to look at our answer choices to see which one has an alcohol and which one has, it would deprotonate. So which one has an ether and which one has an alcohol. So this first one, it only has one ether, so that can't be right. This second one has, B has an ether, but it doesn't have an alcohol, so B can also not be right. So C and D both have one ether, one alcohol. And this one, the ether added to the more substituted side. And this one, the ether added to the less substituted side. And remember, BLAM is how I remember that. Base catalyzed goes to the least substituted side. Acid catalyzed, I don't know what just happened. Acid catalyzed goes to the more substituted side, and this is catalyzed with acid, so that means that it's going to go to the more substituted side. So this is the one I'm thinking right now, but I'm going to go ahead and know that D is also an option. And then E just adds two ethers, so that's not possible because one of them has to be alcohol. So, yep, answer choice C, I'm convinced, is the right one. Okay, next question. The following transformation would be considered what? So if we have an aldehyde and only thing that we've changed is we've added an oxygen right here, adding bonds to oxygen is oxidation. So that is answer choice A. So, and just to kind of go back over the stages of oxidation, if you have a primary alcohol, it will first become an aldehyde. So we took a hydrogen from here and this hydrogen, got rid of them and replaced it with a double bond, or like an additional bond. And then we can sort of do the same thing and go to an carboxylic acid, and we've basically inserted an oxygen right there. If you have a secondary alcohol, you don't have that beta hydrogen right here. There's no, or I guess you do initially, but you only have one option. So the first time we'll get rid of that hydrogen. Nope, that's not what I meant to do. This hydrogen and add a double bond just like we did before. But then there's no hydrogen here, right? The way that we had before, it's just carbons, and you can't move over carbons as easily as you can oxygen. So we stop right here at the ketone. So these are the types of oxidation, and then reduction just goes the opposite direction. That's reduction. So this is oxidation, and these are reduction. So that's just kind of a quick overview that will hopefully help you. Addition is when you have a double bond and you add something to it. Elimination is when you create a double bond, and rearrangement is movement of a carbocation. So none of those are right. So that's kind of how I get my answer. Okay, the next one, again, we start with an alcohol, so one bond to an oxygen, and we end up with 3 bonds to oxygen. So I think this is also an oxidation. Oh, wait. No, I don't know what I was thinking. We start with 3 bonds to oxygen. I'm tired, I guess. And we end with 1 bond to oxygen. And that's why you shouldn't go too fast on your test so that you catch yourself. So I would say this is a reduction because we start with more bonds to oxygen and we end with less. Okay, next question. Which of the following reagents would efficiently accomplish the transformation of cyclopentenone, so that's this, to this? So what I see here is a reduction. We're reducing an ketone, secondary ketone to a ketone to a secondary alcohol. And ketones and aldehydes can be, I guess, let's talk about how there's carboxylic acids, esters, ketones, and aldehydes. So ketones and aldehydes are easy to reduce. These are a little bit harder. So an easy reducing agent, NaBH4, can reduce these two. LAH is a more intense reducing agent. It can reduce all of them. So LAH or NaBH4 could take this ketone to the secondary alcohol. So that's what I'm looking for. I see LAH, so that's one option. And then I see NaBH4. H2 would just get rid of the double bond, so that wouldn't work. So I think the right answer is more than one of these choices. And now this is kind of the opposite. We go from an alcohol to a OH. And then it says, has the starting material been oxidized, reduced, a combination, or neither? And that's not the question. The question is asking what reagent. So that's a typo. I found some typos in your exam too, and I'll announce them before. But so if we go from here to here, the transition is an oxidation. And oxidizing agents, we can use PCC, Jones reagent, or KMNO4. Now each of these have their kind of niche. PCC, it can take secondary alcohol, or it can take ketones to secondary alcohols, no problem. But for primary, if it has an aldehyde, I did that backwards again. I don't know what my brain is thinking. I'm kind of on a time crunch, so maybe that's why. PCC will oxidize a secondary alcohol to a ketone. But for a primary, where there's a hydrogen here, it stops at the aldehyde. So it's kind of weak, so it won't keep going. Jones reagent will take a primary. It also does a secondary to a ketone. They all do that. But it'll take a primary all the way to a carboxylic acid. And so does KMNO4. Now, Jones reagent has a color change associated with it. And then KMNO4 oxidizes everything. It's just out there. I like to say it's effing stuff up. That's what it's always trying to do. It's just trying to mess with stuff. It's Oing things up because it's trying to get oxygen everywhere. So it's just going to oxidize everything. It just messes with everything. But for secondary, it doesn't really, those distinctions between aldehyde or carboxylic acid don't matter, which is what we have here. So we could use multiple of these choices. So the answer is E. Okay, which reagents are capable of reducing the following ester to an aldehyde? So I already drew that up here, is that these will all reduce back to the alcohol. What we didn't talk about is so I'm going to sort of expand this. So NaBH4 will take these to a alcohol. And then LAH will take all of these to alcohol. But what we didn't talk about is how Diels-Alder can take these to an aldehyde. So what we didn't talk about in the earlier question, we did talk about that in class. So if I'm looking at this ester, LAH is going to take it all the way to an alcohol. So that's not our answer because we want an aldehyde. NaBH4 can't reduce it at all. It's not even in the category of being able to be reduced by that. Diels-Alder will take and stop it to an aldehyde, so that's a good option. This, I don't even know what this is, so that won't work. And then H2 that's good at eliminating double bonds, but it's not good at reducing like oxygen. So that's where I think I'll stop. That seems like it's the right answer, so I'm going to go with answer choice C for that. Okay, 15, what is the major product of the reaction of ethyl benzene with KMNO4? I like to call this a spaghetti reaction because it doesn't really matter. Oh, wait, yeah. It doesn't really matter what is on the benzene ring. If you have a benzene ring, as long as it's a primary or secondary alkyl chain, so R group, it'll chop that off and turn it into carboxylic acid. So it doesn't matter what it is at all, it'll turn it into that. So the right answer is answer choice B. Okay, next question. Predict the product of the following reaction. So again, there is, this is a reduction reaction question. And so going back to our carboxylic acids and esters are reduced by LAH. Ketones and aldehydes are reduced by NABH4, and that's what we have. So only these two can be reduced by NABH4, and they'll go to an alcohol. So when I look at the starting material, this looks like an ester, and this is a ketone. So only the ketone can be reduced by NABH4. So no reaction is going to happen over here, but this is going to transition into an alcohol. And so when I look at that, that looks like answer choice B to me, where it, nope, not B. I don't know why I just circled that. It looks like, because this top part can't change. It looks like answer choice 1 to me, A, because the top part was stay the same, and then the second part has an alcohol on it. So that's how I got to that. This one has nothing changed at all, and this only reduced, this reduced both. So this would be the result of what would happen if you had LAH, I think, with it. Okay, 17. What is the hybridization change at the, when a carbonyl group undergoes a nucleophilic attack? Okay, so if you have a carbonyl group, I'm actually going to go back to doing it now back. If you have a carbonyl group, and then a nucleophile comes and attacks it, you've seen this over and over, you get O- plus the nucleophile. So the hybridization here is there's 1, 2, 3 domains, so sp2, 1 s and 2 p's make up 3, and then we still have a p orbital that's left behind. And then over here we have 1, 2, 3, 4 domains, so we must need s and 3 p's to get 1, 2, 3, 4 domains, so that's sp3. So it goes from sp2 to sp3. Okay, 18. Which of the following resonance structures is not a significant contributor to the hybrid for the carbonyl group? So carbonyl groups look like this, and we've drawn this resonance structure a lot, where we get the O- here and the plus here. There's a strong partial positive there. So that's a regular carbonyl group, and then this carbonyl group. Now, the thing that we haven't talked about is a ton in this semester, but you should have talked about it last semester, is resonance structures is not a significant contributor. So the more stable, the more it contributes to the overall hybrid. So you want the more stable thing, and so that means the less charges, the better, and for the charges to be on more electronegative atoms. So oxygen is more electronegative than carbon, so the negative charge being on the negative electronegative atom, that's good. Now the other thing that they have here is one that you probably haven't seen before, where we took our oxygen, or our double bond, and went like this. And the reason you haven't seen it is because this doesn't happen very often, because it leaves this top one without a full octet, and it leaves oxygen, let's see, does it have 1, 2, 3, 4, 1, 2, 3, 4, 5, positively charged oxygen, negatively charged carbon with a lone pair. This is not as stable because the oxygen's more electronegative, so it would rather have the negative charge. So this is not a major contributor. So B is not a major contributor. And you can think that because you've never seen it. You've always only seen this positive charge or a partial positive right here. So that's kind of a quicker way, but then also if you know the resonance theories, that also will help. Okay. Next question, if we have this ketone with LAH, what happens? So H- will come and attack and kick up. CH3, O-, and then we have our H there. And then if there's a good leaving group, the carbonyl will restore, but there's not a good leaving group. So the only thing that is going to happen would be we add our acid. So this goes and takes the acid from the H+, and that's it. So this is what I'm looking for. So I'm going to go through all of these. Also, I will say, because it's a carbocation or partially like an sp2 hybrid to an sp3, you're going to get a racemic mixture. So you'll get this plus the enantiomer. So let's see. But the other side, this one, the stereochemistry on this shouldn't have changed. So when I see the stereochemistry on that, I'm going to make sure this one hasn't changed. So B is wrong because something changed at this carbon where, here, let me actually highlight it. Something changed at this carbon, but no reaction happened at that carbon, so that doesn't make sense. And then the same thing here with D. Something changed at that carbon, but no reaction happened there, so it didn't make sense. So I'm narrowing it down to 1 and 3. And 1 and 3 both look right to me. They're just enantiomers of each other, so they're both versions of this. So I am going to say that we'll get a mixture of 1 and 3. So that's answer choice B. Okay, question 20. Your task is to synthesize this molecule through a Grignard synthesis. Which pairs of compounds below would you use as starting material? So, first of all, Grignard, if you have a bromine, you're going to put magnesium in. And then it's going to become negatively charged right there. It's essentially just a negative carbon right there where the bromine had been attached. And then that acts as a good nucleophile, so it will attack. Oops. It'll attack and kick up, or it'll attack and kick up. So for all of these, we would get O- from what used to be there, plus a bond to our new structure. So in this one, the O- is adjacent to the 5-membered ring. So you see the O- that will eventually turn into our OH right here. Right here. That is on the 5-membered ring. Here, this is 5-membered, but it should be on a 6-membered ring. So that one is wrong. This next one, it looks like we have our O-, and then that's bonded to a 5-membered ring. This is a promising option, but I'm going to try all of them. This has 2 6-membered rings, but we have a 6-membered ring and a 5-membered ring, so that can't be right. And this has 2 5-membered rings, but we have a 6-membered ring and a 5-membered ring, so that's also not right. So answer choice B is our only option. So even if you didn't know how Grignards react, if you could just notice that there needs to be one reagent with 5 and one reagent with 6, you could have eliminated C and D and gotten yourself closer to the right answer. So whenever I say, you know more than you think you do, that's what I mean, is use the information that you definitely know to eliminate wrong answers. Okay, next question. The HOMO of the butadiene radical has how many electrons? This should have been, I think, the propane radical. Propene, because butadiene radical, it could have been anywhere, and there's only one double bond, so that is wrong. I said that wrong. Or actually, more accurately, it probably should be of the allyl radical. So for questions like this on your test, I'll make sure that that's not worded wrongly. But so the allyl radical has how many electrons in its ground state? So when we're looking at that, we first identify p orbitals. So all 3 of these are sp2 hybridized. And I have a whole video on hybridization that you can go watch if you're not sure. So each of these have a p orbital. So this is a p orbital. And so each of these p orbitals will be stacked up like this, and then we count the number of electrons. So this double bond has 2 electrons, and then this radical is 1 electron. So we build in from the bottom up, and it looks like this. And now I'm going to label the HOMO. The highest occupied molecular orbital is the highest one in energy, so the energy is going up. So literally the tallest one that still has an oxygen or an electron in it, and then the lowest unoccupied is the LUMO. So this allyl radical has, let's see, 1, 2, 3. It has 1 electron in its ground state in the HOMO. And then the next question is how many pi orbitals are in butadiene. So there's sp2 at each of these locations. So each one of these has a p orbital left over. So there's 4 p orbitals in that. And there's definitely questions on that on your homework where we did conjugated systems, and on tests from that as well. Okay, which of these is not an example of resonance? So let's see here. If this moves over, this is an example of resonance. Oh, it's asking which is not. So this one. If the electrons move here, then that is. This one, no change happens. So this one, there's no double bond. So this is, I don't understand how, nothing moves but this positive charge. Just this positive charge moves. No double bond, nothing trades places with it or anything. So these are just 2 different carbocations. And then this one, the electrons could move here and go here. So that is resonance. So I guess answer choice C would be the one that's not resonance. And if you need to review, I do have several videos on resonance that are linked on my link tree. If you go to linktr.ee/organicmelissa, there is a page that is just all of my videos by chapter. So and they have topic as well. Okay. I'm actually going to pause here because it's my office hours. Well, let me open my door, and if anyone comes in, I'm going to have to pause. Okay, so I'm going to keep going on this video, and if any students come to my office hours, I'm going to have to pause and start a new video. Okay, which alkene would you expect to have the lowest heat of hydrogenation? So the most stable is going to be the ones that are most conjugated. So the more in conjugation, the better. So I like to sort of highlight all the p orbitals and see how many of them are connected. So this has 4 p orbitals that are connected. This right here has 1, 2, 3, 4, 5, 6 p orbitals that are connected, so that's a good option. 1, 2, 3, 4 p orbitals that are connected. These 2 are off to the side, so they're not connected. Same thing was happening here. So 4. 1, 2, 3, 4. 1, 2, and then a split, 1, 2, and then a split. Okay, so of all these, the answer choice 2 has the most conjugated, so that is going to be the most stable of these alkenes because they can share the electron sort of on this highway that opens up. Instead of the double bond just concentrating the extra electrons in one place, they can kind of spread it out, and that's why it's more stable. Okay, which of the following dienophiles is most reactive in a Diels-Alder? So a Diels-Alder reaction, I'm going to add in a page. Diels-Alder reaction looks like this. And basically this diene acts as the nucleophile. And so it attacks, and then this thing will come and attack here, and then this bond will move over, and you end up with this structure. Now I always like to number 1, 2, 3, 4 come from the diene, and then 5 and 6 comes from the dienophile. So that kind of helps me just keep track of what's going on. So since this is the nucleophile, more electrons are better. So more electron density is better. And then over here, this is the electrophile. It's called a dienophile because it wants a diene. So more electron withdrawing groups, less electron density is better here. So when I look at this question that's asking which of these Diels-Alder reactions is most reactive, which dienophiles, well, first of all, a dienophile, we want it to have less electron density. So that means more electron withdrawing groups. So methyl groups are electron donating. There's extra electrons here on it being a triple bond. It could act as a dienophile, but again, more electrons. Here we also have methyl groups, so electron donating. Cyano groups are electron withdrawing, so this is a good option. And then the oxygen here is going to be electron donating. So I think it will be answer choice D based on that. Okay, which of the following pairs of compounds could be used as the basis for a Diels-Alder synthesis? So again, when I think of Diels-Alder, I know it always makes this 6-membered ring with an alkene. 1, 2, 3, 4, 5, and 6. And these bonds weren't here. So it started out like this. 1, 2, 3, 4, 5, 6. So I'm going to identify the 6-membered ring with the alkene right here. And I'm going to say this is 1, 2, 3, 4. And then down here, 5 and 6. 5 and 6. And then I'm going to just add the things that were on this between 1 and 2. This looks wonky, but 1, 2, 3, 4, 5. So see how I still have 1 and 2 have this ring around it, 1 and 2. 3 and 4 have this ring around it, so 3 and 4. And then 5 and 6 has this COOCH3. So I'm looking for a structure that looks like this and a structure that looks like this. Now this one here is tempting, but this is what it looks like after it's formed. It has to start as a diene. So it has to be 2 double bonds. So that one can't be right. And then these other ones, they would undergo a Diels-Alder reaction, but it wouldn't end up looking like what we just drew. So I think the only answer choice is D. If you want to challenge yourself and go a step further, you can have this CO2CH3 and test yourself and see what they would make. So like this one, this is 1, 2, 3, 4. And then this is 5 and 6. So 1, 2, 3, 4, 5, and 6. So 1 and 4 have this bridge over it with this crazy CO2CH3 here. And then 5 and 6 have a methyl there. So you can test yourself that way and see what would it make. Or you can just answer the question. But sort of seeing why the wrong answers are wrong, I think sometimes helps. Okay, what would be the product of the following reaction? So again, I see this double bond, this diene with a dienophile like this, and I immediately think this is a Diels-Alder reaction. So this goes here, this goes here, this goes here, and we're going to get our 6-membered ring. So 1, 2, 3, 4, 5, and 6. So there's a bridge between 1 and 4. And then on 5 and 6, we have the COCH3. So this is what I think it's going to end up looking like. And so I'm going to look for something similar to that. This doesn't even make a 6-membered ring, so that can't be right. This makes a 6-membered ring, but it doesn't have the alkene in it, so that can't be right. So I can immediately eliminate 1 and 2 because they don't make what the Diels-Alder product makes. So you can, again, eliminate wrong answers. Diels-Alder needs a 6-membered ring with an alkene in it. So you can eliminate wrong answers and get down to here and here. Well, the difference between these two is this has 1 carbon bridging between 1 and 4, and this has 2 carbons bridging between 1 and 4, but here we only had 1 carbon between 1 and 4, so this one's not right, and this is our right answer. Identify the structure of 4-amino-bromophenol. So phenol is OH, And then that would be 1, 2 bromo, 3, and then 4 is the amine, so NH2. So I think it looks like this. So all of these have an alcohol. Oh, this doesn't have an alcohol, so I can eliminate those. So if I just know that phenol is an alcohol, I'm already going to be able to get it down to 3 answer choices. And then between these, they all have an amine and a bromine. So the OH and the BR need to be 1 apart, 1, 2, so that one's wrong. And then can you just count to 4, basically? 1, 2, 3, 4. So this is the right answer. Answer choice B. Okay, and if you're wondering why do I go around the ring this direction and not this direction, it's because alcohol was 1 and bromine was 2. So you have to keep going in that direction. So the next one has to be 3, 4, and this one would be 5. If we went this way, it'd be alcohol 1, carbon 2, amine 3, this carbon would be 4, 5, and bromine 6. So if you're going to go 1, 2, you have to keep going in that clockwise direction because that's how you started. Okay. Now identify from the following compounds which one is anti-aromatic. So Huckel's rule says that 4n plus 2 pi electrons, so n is any whole number, so it could be 0. 4 times 0 plus 2 is 2. 4 times 1 plus 2 is 6. 4 times 2 plus 2 is 10. These, if you have these number of pi electrons, it's going to be aromatic. If you have 4n, so 4 times 0 is 0, 4 times 1 is 4, 4 times 2 is 8, it's going to be anti-aromatic. So we're looking for something with 4 pi electrons. So, and something else that helps is drawing in your lone pairs. So I recommend you draw in your lone pairs on a question like this. Oh wait, boron actually does not have any lone pairs. Because it comes with 3 valence electrons, if you remember. And so it's neutral right here, which means that 1, 2, 3 is all it has. And you can remember that based on looking at the periodic table. It's in the 3rd column. Okay, so I draw in my valence electrons. The next thing I check for, if you remember, aromaticity and anti-aromaticity require an unbroken chain of p orbitals. So the first thing I notice about question 5 is it's sp3 hybridized right here, which means there's no p orbital there. So all the rest of these, though, they look like they have a lone pair, or like this has an empty p orbital. So all of these are good options. And then the other thing you have to remember is if one of these can go in the p orbital that's parallel to the others, you can only have 1 p orbital from a lone pair at a time. So this other one will hybridize. So there are actually, lone pairs are tricky. Double bonds are easy to sort of tell how many pi electrons. Each double bond contributes 2. So there's 1, 2, 3, 4 here. 1, 2, 3, 4 here. 1, 2, 3, 4. 1, 2, 3, 4. So each of these gets 4 electrons from the bonds, and then we have to look at the lone pairs. So only one lone pair can contribute, the other one will hybridize. And we have a bunch of talks about that when we actually went over this. Hybridize. So I'm not going to go completely over it now, but if you're not sure, go back to the homework on that. And then we had like a whole class period where we just talked about lone pairs and aromaticity. But only one at most will contribute. And so for all of these, we get 2 electrons from the lone pairs. There's no lone pairs here, though. So this is all of these have 6, so all of these are aromatic. This is the only one that's anti-aromatic. So be sure that you know how to do heteroatoms with aromaticity. And I think I have some shorts on these, but I also have some longer videos, and then lone pairs. We learned this towards the very beginning of the semester, so this is probably going to be hardest for you to remember. Okay, next question. Identify which one is non-aromatic. So this would be lacking a continuous pi orbital. Or if it has eight or more electrons. But I'm looking at these and all these look like they would be aromatic to me. Because this has 6 electrons and an unbroken chain of p orbitals. There's one at each one of these. This has, oh, I see why. This has an unbroken chain of p orbitals through here, but this is sp. This nitrogen has 3 bonds to it, so it's sp3 hybridized. So this one does not have a continuous chain of p orbitals, so answer 2 is the answer there. The next one, identify which one is aromatic. So this wants 6 electrons and a unbroken chain of p orbitals. So that's the first thing I check for is the p orbitals. This has an unbroken chain of sp2 hybridized. Same here. This is sp3 hybridized, so that one's out. This is a continuous chain, and this is a continuous chain, so great. The next thing I'm going to look at is electrons from bonds. So this gets 2 electrons from bonds each side, so that's 4. This is also 4. This is 4 electrons from bonds, and this is 6 electrons from bonds. And then there's a lone pair up here. Okay, and then let's look at lone pairs. So this gets none from lone pairs, so this is anti-aromatic. This gets none from lone pairs, so this is also anti. This could get 1 pair from this heteroatom lone pair, so +2, so this 6, so this is a good sign. This carbanion has 2 lone pairs, so this is 8, so this would be anti, or if it could bend out of the shape, it would be non-aromatic. So this is answer choice D. Okay, the correct name for the compound shown below is, for these, if you remember the common name, that's great, but you should remember the common name of aniline is NH2. Okay, I'm going to pause this recording and come back to it.